In this video, we present the clinical application of computer assistance. Heart valve disease is a major public health issue, with over 13% of the population over 75 years old presenting significant valve disease. Currently, the vast majority of heart valve surgery is performed using biological heart valves, also called bioprosthesis. Regardless of their brand, all stented bioprostheses are built around biological leaflets, a supporting stent, and a sewing ring. The major trade-off of bioprosthesis is their limited durability, due to what is called structural valve deterioration, or SVD. It occurs over time, mainly through wear and tear or calcification of the leaflets, or both, leading to the dysfunction of the valve. However, as we have demonstrated, SVD does not alter the stent and the radio-opaque landmarks of bioprosthesis. SVD may be treated with transcatheter valve-in-valve implantation. The procedure is carried out under fluoroscopy and relies on the precise implantation of a transcatheter heart valve inside the degenerated biological valve based on its radio-opaque landmarks. Our approach was based on the modelization of radio-opaque landmarks of the bioprosthesis, which allowed us to create a library of surface meshes of bioprosthesis. Based on this library, the surface mesh of the corresponding valve is chosen, and the optimal level of implantation is added to the surface mesh to guide the implantation. In this case, of a mosaic valve, the main challenge is due to the lack of radio-opaque landmarks, namely 3 radio-opaque islets at the top of the commissures. This is where our homemade software is used, based on the live feed of the fluoroscopic images from the hybrid operating room. Our software is designed to allow real-time registration and tracking of the surface mesh onto the fluoroscopic imaging. Our software uses as input the live fluoroscopic streaming to acquire an initial video sequence. From that sequence, we choose an image suitable for both registration and tracking, i.e. an image where the radio-opaque landmarks are clearly visible and do not present any conflict with other radio-opaque structures. Once this image is chosen and the radio-opaque landmarks clearly identified, a bounding box is set up that will allow the template tracking. The registration is a classical 3D 2D registration based on 3 radio-opaque landmarks. It allows the superimposition of the surface mesh onto the fluoroscopic image. Finally, this is the augmented fluoroscopic view demonstrating the surface mesh alongside the optimal implantation level superimposed on the fluoroscopic image. The transcatheter heart valve is implanted while maintained alongside the optimal implantation plane. This plane is crucial for both clinical and technical outcomes. The constant monitoring through the tracking allows a permanent superimposition of the image and mainly a permanent alignment of the transcatheter heart valve with the implantation plane. The angiographic evaluation after implantation demonstrates optimal implantation with no residual regurgitation. Thank you for your time.